Yikes. Okay, guys, so I hit stop instead of pause. So anyways, that was a very short video. Now we're on to video number 4. All right, but I have my calculator now. So what's our new K then? So it's going to be 6.8 e to the negative 4 squared. And we get 4.6 times 10 to the negative 7th. All right, so we have one of them. Okay? And we're just going to call this like step 2. All right. Okay, now let's take care of the last part. So we need an oxalate ion on the left. This reaction gives me 1 mole, but it's on the wrong side. All right, same thing here. It gives me the 1 mole of oxalic acid I need, but it's on the wrong side. So for this one, I'm going to need to flip it, right? Okay, so again, remember, line up your arrows. That makes your life 10 times easier. So we have 2 protons plus the oxalate ion gives me oxalic acid. Okay. And then circle, 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 circle. I'm there, right? And guess what? The one thing I didn't need cancels out, so it's perfect. Perfect. All right, so then let's talk about the K of this guy. So this K was 3.8 times 10 to the negative 6. But what did you do to this? You flipped the reaction. Okay? And if you flip it, then the new K, what do I have to do? It's a fraction and I flip the fraction, so I need to say 1 divided by the original K. So 1 divided by 3.8 times 10 to the negative 6. Got to take the inverse of it. So 1 divided by times 10 to the negative 6. And we get 2.6 times 10 to the 5th. You double check that. 1, 2, 3, 4, 5. Yeah, to the 5th. All right. So this is for step 1. Now, how do I manipulate the two together? I'm not going to add them. I'm going to multiply them, okay? So 4.6 times 10 to the negative 7th times 2.6 times 10 to the 5th is, put that in your calculator, 4.6 e to the negative 7 times 2.6 e to the 5th. And I get 0.11 in sig figs, right? And if we go to the slide, close enough, right? Actually, no, I'm sorry. I got 0.1196. Dr. Stover made a boo-boo. She should have rounded that. So 0.12. 0.12, which is exactly what the slide says. My bad, guys. All right, not perfect. All right, let's do another one. Whoop, nope, go away, answer. All right, so manipulating this one. All right, now what's sort of the shortcut method here? Well, you could just look for the major things that you need that only exist in one of the equations, right? So if we consider the fact that we need, say, carbon dioxide gas, we have to have it. All right, only one equation gives that to me, right here. Sorry, screen's messed up because of my hand. CO2 gas as a product. So I'm going to have to flip that. And that's good because that's also going to move my water vapor to the right side. So basically, reaction 1, I need to flip. Okay? So let's go to our handy dandy paper. Get the thing to hold it. All right. So for the first reaction, which was 1.0 times 10 to the 5th, right? We needed to flip that, right? Because we're going to flip the first reaction, okay? And then we're going to multiply, right, that by the second reaction. What do we need to do to the second reaction? You may be thinking that we're going to have to do something because of the H2, but remember, we got an H2 moved over here, so we are going to have 3 H2s on the left as that stands. And the methanol lines up, so we don't really need to do anything to this, right? So it's just going to be the 1.4 times 10 to the 7th. That's it. All right, we just got to put that in our calculator. So 1 divided by 1 e to the 5th times 1.4 e to the 7th. And I get 140. Or in proper sig figs, I guess that would be 1.4 times 10 to the 2nd. Right? But there you go. So you can work it out and you can prove to yourself that everything cancels, or you can just work through it and assume that it's all going to cancel. It's up to you how you want to go about it, all right? But I showed you sort of both methodologies to go about it. We're going to stick with this mode for now because why not? We've got time. All right, so I already mentioned that KP was going to pop up, right? And literally the only difference between KC and KP is the fact that KC is concentrations and KP is pressures. So we're not going to use brackets anymore. We're going to use kind of like the symbol for partial pressure. So the pressure for C raised to its coefficient. The pressure of D, the partial pressure of D raised to its coefficient, divided by the partial pressure of A raised to its, divided by the partial pressure of B raised to its coefficient. Okay? So it's just slightly written a different way, but when it all comes down to it, it's the same expression. Nothing has really changed. Now, but how do we relate KC to KP? Like, what if you know one and you want to know the other? They're not necessarily equal numerically. So let's talk about that. So let's first talk about how we might relate the two together. Well, why not go to Pivnert, right? So think about what concentration is. Concentration is moles of a solute divided by liters of a solution, right? Well, you got N right here, and you got liters right there. So why not rearrange this to get N over V, right? And what we've done here is we've solved it for P and concentration at the same time. So the partial pressure with respect to A is equal to the concentration of A times RT. And this is what leads us to the equation that relates the two to one another. Don't worry about all this, like being able to derive it. You guys know I don't really ask you to derive equations. I just ask you to be able to use them. But this equation right here, you need to have this memorized. Have this equation memorized. So KP is equal to KC times RT. Now, what are? We're talking about gases here. So don't use the 8.314. Use the 0.08206. All right? Go back to that old school R. All right? And if R is 0.08206 liter atmosphere time mole Kelvin, what are the units of temperature? Kelvin. All right, and then delta N. Delta N is moles of gas product minus moles of gas reactant. So what are we saying? We're saying that we don't care about any phase that isn't a gas as far as delta N is concerned. All right, so what does this mean? This means that the only way in which KP and KC are equal to one another is if delta N is 0. Right? Because anything raised to 0 becomes 1. Right? 1,000,000 raised to 0 is 1. So if you have 2 moles of gas reactant and 2 moles of gas product, then KP equals KC because delta N is 0. But KP only equals KC when the moles of gas on either side of the equation are the same. If they differ, even by 1 or a half a mole, KP will not equal KC. Now, does this mean they're going to be dramatically different? No, they should be in the same ballpark as one another, but they're not going to be exactly the same numerically. Let's do an example. All right, so I'm going to pause the video.